welcome to the QuiC Talks, Quantum Information and Coherence Talk. These are supposed to be talks covering broad areas and more modern areas in quantum information and coherence. This is actually the last talk of this semester, and we are glad that today we have Professor Andrew Forbes from University of Witwatersrand, Johannesburg, South Africa. The title of his talk, which looks quite exciting, is Quantum Mechanics with Patterns of Light. Well, maybe not just a few words, maybe a few more words. This is one of the best, very interesting biography, I think I'll say. I'll read the whole thing. So this is a very interesting and motivational biography, so let me read it. So Professor Andrew Forbes, he has at various times in his career found himself as teacher, janitor, secretary, receptionist, webmaster, system engineer, sales rep, manager, director, and sometimes a scientist. I think the last part maybe is kind of an understatement. But so Professor Forbes, he is presently a distinguished professor within the School of Physics at the University of Witwatersrand, where in 2015, he established a new laboratory for structured light. He is an active He's active in promoting photonics in Africa, a founding member of the Photonics Initiative of South Africa and initiator of South Africa's Quantum Roadmap. He is a fellow of SPIE, the OSA, the SAIP, and an elected member of the Academy of Science of South Africa. He holds an A rating by the South African NRF, 3 honorary professorships, is editor-in-chief of the IOP's Journal of Optics, and sits on the editorial board of 3 other international journals. He has won several awards, including the NSTF National Award for his contributions to photonics in South Africa, the George Forster Prize for the Alexander von Humboldt Foundation for outstanding contributions to photonics, and the SAIP Gold Medal, the highest award for physics in South Africa, making him the youngest winner to date. He spends his time having fun with the taxpayers' money, exploring structured light and lasers, as well as classical and quantum optics. So again, we welcome him today, and we are looking forward to a very exciting talk. So over to you, Professor Forbes.
Thank you very much for that very kind introduction. I don't normally let people read the bio, but that's very kind of you to say it. And for the students, let me tell you that it's all true, actually. Earlier in my life, when I finished my PhD, I didn't do a postdoc, which would be the normal thing to do. I started a company with my friends. And so we started to sell lasers. And if you've ever have the opportunity to be in a small startup company, you will discover that you do everything. You really are the receptionist and the everything under the sun. So it's all true. All right, so thank you. So I've made the talk very general. It's going to cover some basics as well as some of our own research, but I'm going to point you towards the end in the direction of some wonderful research work by other groups. And hopefully you can read more widely than what I'm going to show you today. So I'm at Wits University, but before I show you where that is, let me tell you where I am. So here is South Africa. We're at the bottom of the continent. Actually, one of my honorary professorships is here in Stellenbosch, near Cape Town, very pretty. I grew up in Durban. It's a surfing town, it's a beach town. And actually, it's also where Gandhi grew up. And the Indian population in Durban is probably about 50%, I would say. So lots of very good curries. I now live in. Sorry, there's a very bad echo.
Yeah.
Is that better now?
It should be fine
now. Okay, all right, good. I live just outside Pretoria, which is the capital of the country, but the university is in Johannesburg. But it is the financial capital of South Africa. So if you come to Johannesburg, actually, it's the largest man-made forest in the world. So this is the suburbs of Johannesburg, but you have to come into the city center to find the university. And when you do that, then this is an example of one of the buildings on the campus. So it's pronounced Wits with a V because it's a Dutch name. And the direct translation would be a rand of white water because there's a big aqueduct under the city. And next year, in fact, the university will celebrate 100 years, our centenary. Well, if you come a little bit to the left of this great hall, excuse me, then you find the School of Physics. It actually looks very similar to this. And in the School of Physics is my lab, and we play with structured light. Traditionally, we make structured light with digital holograms, but I'm going to show you a range of techniques to do it. So let me begin with a one-slide tutorial on what I mean by structured light. So imagine that I have this blob of light. Could be a Gaussian beam, could be anything, it doesn't really matter. But let's say I have this blob of light, and I would like to convert it into something else, maybe a smiley face. And what we ask is, what is the optical that I need to put in between what I have to produce what I want? And now the answer to the problem and the way you implement the answer, they typically are coupled in some way. So for example, you could say, well, why don't you just take a piece of glass and a black pen and block out everywhere you don't want light. So everywhere you don't want light, you block it out and you let light through everywhere else. Well, that would be an amplitude mask, and indeed you would get a smiley face. But you can see that that would be very lossy. You would throw away a lot of your light. So instead you could say, well, look, everywhere I want light, I want constructive interference, and everywhere it's dark, I want destructive interference. So what should the phase pattern be that would make that possible? And when you calculate the phase, of course, you can choose to implement it as a metasurface or a diffractive optic or a digital hologram. And although I've shown this for the amplitude of light, the same principles can be used for all of light's degrees of freedom. And so that's what we try to do in structured light. We try to control all of light's degrees of freedom and tailor them for the applications that we have in mind. Now, I said traditionally we use digital holograms, and in this talk, I'm going to talk about digital holograms quite a bit. So let me take a slide or two to explain what sort of tools I'm going to. So a typical tool in our lab would be a spatial light modulator. Perhaps you have some in your lab as well. And it's typically about 2,000 by 1,000 little liquid crystal pixels. Inside each pixel are these liquid crystal molecules. They can rotate with an applied voltage. And depending on the rotation, by form, by refringence, I get a phase change. So for the remainder of the talk, you can assume that we've calibrated the devices very nicely, and that if you see a color black, it means that the applied voltage gives you no phase change. And if you see the color white in the picture, it means that the rotation is such that you get a 2 pi phase change. Actually, modern devices can go all the way up to about 9 pi that I'm aware of. So it doesn't have to be limited to 2 pi, but for this talk, we will calibrate it to 2 pi. And now you can actually do some Fourier tricks, which I will explain in 2 slides from now, to make this phase-only device also control amplitude. So actually, this is the hologram that produced this experimental smiley face. And what is less known is that you can make it work across a wide band of wavelengths. You lose a little bit in efficiency, but the function of the hologram still remains. And if you want to know more about that, we have a little handbook that gives you all the MATLAB code to get started. I think SPIE make all the money, and we get like 1 US cent every time you buy a copy. But in this book, you can find all the tutorials and the code to get started. These days in our lab, we've switched a little bit towards digital micromirror devices because they're faster and they're cheaper. So all these are, you can strip them out of any projector that you might have, like a data projector. This is what you would see. And if you zoom into the screen, you will find these little MEMS mirror. And these mirrors are very simple in their functionality. They can essentially switch on or off. They can direct the light, say, to the left or to the right. And that would be representation of an on or an off state. And so they can only modulate amplitude. So how can you make an amplitude device do phase and amplitude? And likewise, how do you make the phase device do phase and amplitude? And I'm going to explain it just with some high school mathematics. The rest of the physics is quite straightforward. You know from your mathematics that if I take a function like e to the ix and I add e to the minus ix, well, then I get something that goes like cosine x. But what I want you to notice is that on the left-hand side of the equal sign, everything is a phase function. And on the right-hand side, everything is an amplitude function. So herein lies the key to making amplitude work for phase and phase work for amplitude. And the way it works is that the X, of course, means something, and the plus or the minus, this minus and the plus, has physical relevance in the optical world. In the optical world, the plus and the minus tells you where to look. They represent diffraction orders. So for example, if I make my capital X here, say a desired phase with a grating, so angle the lights, then the minus and the plus will tell me that what I want appears in the +1 order, and the negative of what I want appears in the -1 order. So I just have to know where to look. If I look at the right place, I can make amplitude devices do phase. And so by playing these tricks, I can go back to my very simple projector. And here you see an experimental video of some structured lights, very complex structured light fields, but created on a very simple device. And so you can use all these tricks to make, in fact, any beam or structured mode that you want. And here are some examples of structured light modes with the associated hologram. And so all you need to now is go back to the lab. And this is one of my former students. She's now a researcher in her own right. So it's Angela, and she's, in this case, using a very old spatial light modulator. And she's playing these tricks. And with the long exposure, you can see that we've generated a donut beam. And so this is now one of our structured light fields. But now everything I've told you so far, of course, has been classical. And so how can we make all of this work in the quantum world? So in our lab, we use a very vanilla form of creating entangled photons. What we do is we illuminate a nonlinear crystal with a UV photon. When I say UV, I really mean just a high energy photon. The wavelength could shift. In our lab, actually, we use some green photons or infrared, so not infrared blue, or actually ultraviolet. But if I come in with a high energy photon, say a UV photon, if I engineer the phase matching correctly, I can produce two infrared photons that are correlated in their momentum. And so now I've got entangled photons, and the question is, in which basis should I express this entanglement? And that's where the patterns of light come in, because I'm free to choose the basis that I want. So here's my cartoon again of the entanglement experiment. I'm going to excite a crystal. Doesn't have to be BBO, but could be. And I'm going to generate two entangled photons, and I'm going to choose to express the entanglement in the basis of patterns of light. So you see that here I've got the Hermite Gaussian modes. Of course, I've got two indices. The Laguerre Gaussian modes also have two indices. They form a complete orthonormal basis. And so they are perfectly valid for expressing entanglements. And that's what I mean when I say quantum mechanics with pictures or with patterns of lights. This is going to form the basis in which I express that entanglement. So let's take a moment just to convince ourselves that we really are going to have entangled photons. So here is my pump photon coming to some nonlinear crystal. I'm going to try to generate two entangled photons. Why would it happen? Well, the phase matching conditions allow me to dictate that I'm going to conserve energy and momentum. And so that means that by tuning the crystal, I can tune how this phase matching works. And here you see a camera image of the down converted photons. So in fact, if I select the two photons on the edges, you know, they would have momentum of a plus and minus. So I have entanglement. Or I could tune the crystal to be collinear so that all the photons are traveling together, and I can find my two entangled photons in the middle. And you might say at this point, but where is the entanglement? Well, if I place filters at the back end of my detectors so that the momentum that I measure, which is dictated by a wavelength band, if that wavelength band allows many different momentum values, then if you write it out, you can see that you have a non-separable state. So in other words, It's quite a lot of background noise. I'm sorry, I don't know. Maybe somebody should mute. So the momentum of the two photons must add up to the pump. So if photon A has got a momentum of K1, then photon B must be Kp minus K1. But photon A could also be K2, and then of course photon B is Kp minus K2. And so you can see that you have a large sum of momentum combinations, which means you have a superposition in linear momentum. And so this establishes the entanglement, and now it's just a question of expressing it on whatever basis you want. And in fact, you can visualize the conditions just right. Here you see the SPDC pattern actually captured on a little smartphone, and so it can be very bright under the right conditions. And this is taken in our lab. For the students who haven't done a quantum experiment before, let's...
Just one quick, is that picture real? The colored one?
Yes, it's real.
And that is taken with the smartphone?
Yes.
Wow, that is very impressive. I see.
Yeah. I have to tell you that we've only seen this about once in 10 years. So it's not, we don't see it every day. You know, yeah. We were also very surprised to finally see it, actually.
So these are using filters, different shots, or just a single shot with a smartphone?
This is just a continuous wave pump. So it was actually on the wall of the lab, and we could capture it with the phone. Yeah.
Wow. Well, I will try it.
Yeah. So this is a direct photo. This is actually taken on a piece of paper, the beam on the paper.
Nice. Very nice. Excellent.
Yeah, it's very nice. So for the students who've not done one of these experiments, let me give you an indication of how poor the efficiency is. So imagine that I have a pumped source, a pulse source, not continuous. Actually, we use both in our lab. And so packets of energy arriving at the crystal. And it depends on your laser, but let's say in our lab, it might be in the order of about 1 billion photons per little pulse of light. How many of these get converted into an entangled pair? Well, on average, in this pulse, we find none. And in fact, in our lab, if we go to the low energy regime, we have to wait for about 10,000 of these pulses to pass through to find one entangled pair. So the efficiency of this SPDC process is very, very low. And so that's why sometimes you'll see that people use a mode-locked laser in these experiments. And that's not because they need short time pulses, it's because you need a high repetition rate. Today we use mode-locked lasers and we use continuous wave lasers in our experiments. So let's just move away a little bit from the cartoon to something a little bit more specific. So here would be an example of one of the experiments in our lab. We actually have 4 quantum experiments running. So in one of them, we have a mode-locked 355 nanometer laser. It's pumping a BBO crystal. We also use periodically poled KTPs and so on, but these are very nice because you can just tune the angle. And we might put a camera in the path. If you have a nice Spiricon camera with good gain, you can actually see inverted light. So this is what it looks like on a normal CCD camera. You decide based on the angle whether you want to work with colinear or non-colinear setup. If it's colinear, you might split it with the beam splitters. So one photon gets directed one way and the other one the other way. Of course, you also sometimes get 2 going one way, but then there's no coincidences. And we're going to direct them to spatial light modulators in path B and in path A because we want to measure the patterns of light. And then we'll couple them into fibers and avalanche photodiodes and measure in coincidence. So this is a bit more realistic in a cartoon from what I've shown you up to now. And then this would be what an experiment in our lab might look like. Actually, this is a 4-way coincidence experiment, so it's a little bit more complicated than the usual one. But in principle, you see, it's what my wife says, it's Meccano sets for grown-ups. Let you play around with nice toys that children like to play with. I once had a student who asked me, what does all of this stuff add up to? How much does it cost? So in a typical quantum lab, you need a nice laser, you need some nice detectors, you're going to play with patterns of light, you need a spatial light modulator, and you need some instruments to do your coincidence counting. And if you add up the value of all these things, my student told me, he said, what? But that's the same as a Maserati. So indeed, you know, we choose to buy toys rather than cars. And I promised him one day I would actually try to put the car into my grants. But I don't think the South African Research Foundation would give me money for a Maserati. All right. So a lot of money on the table, sophisticated experiments. We want to play with patterns of light. What pattern shall we choose? So of course, our favorite pattern is orbital angular momentum. For several reasons, it's very intuitive, it's easy to measure. It actually also forms a natural Schmidt basis, so it's very useful from a theoretical point of view. So I'm sure you know what orbital angular momentum is, but let me give you a one-slide tutorial anyway. So here's a Gaussian beam, the blob of light I showed you earlier. It doesn't have any orbital angular momentum, and it has planar wavefronts. Well, at least by the waist, right? Of course, if it propagates, the wavefront can become curved, but let's just assume we're near the waist plane, the wavefronts are plane. And now what I'm going to do is I'm going to take that planar wavefront, I'm going to give it one twist per unit wavelength. And then if I do that, I get this donut-like beam with an intensity null in the middle. Why is there an intensity null? Because the phase is not defined on the axis. Or if you want to think about it differently, the spatial frequency becomes so high that it can't support light in the optical system. And this beam carries 1 h-bar per photon of orbital angular momentum. And if I, instead of twisting once, I of course can twist it twice or 3 times, you see that the donut gets bigger, the hole in the middle gets larger, and the phase front becomes a little bit more complicated. I once had a Russian visitor to my lab, and he said to me, why do you care about how complicated the phase looks, because you don't even have any light in the middle of the beam? It was a very pertinent question that took me a while to think of an answer. But you would have noticed that I've been twisting clockwise, but you can also, of course, twist anti-clockwise. So instead of going all the way to positive infinity in the one direction, you can go negative infinity in the other direction. So if I bring this into my entanglement cartoon, I'm now going to specify a little bit more detail. I still have my pump UV beam. I've still got some nonlinear crystal, but now I'm going to specify any orbital angular momentum to begin with. But we know that orbital angular momentum must be conserved, which means that the OAM of the photon A and photon B must add up to the pump, so it must add up to 0. And now it's a simple primary school math question. How many ways can you add 2 numbers to 0? Well, I could have one of them as +1 and the other one as -1. That would work. Or the other way around. Or I could have one of them as 2 and the other one as -2, and so on. And so in fact, if I write out the combinations, then I get this high dimensional states that has all the possible sums that add to 0. And this also is a non-separable state. And so you see that in the orbital angular momentum basis, we see that we have not only an entangled state, but a state entangled in high dimensions. In principle, infinite dimensions, but we'll come to that in a second. Just for completeness, I want to tell you that it doesn't have to be that the pump has no angular momentum, and it doesn't even have to be in orbital angular momentum mode. There's been a lot of amazing work in structuring the pump to structure what the entanglement looks like. And if you want to know more about that, you can read actually a recent article that we wrote on this topic. All right, so let's look at the back end of our cartoon. We're sending these 2 photons to spatial light modulators, which are connected to these detectors. But how do we measure a pattern of light? I showed you in the early slides how we could create patterns of light, but how do you detect patterns of light? And so again, I can explain to you the concept in a single slide. Remember, I told you I'm going to start with a blob of light. I'm going to send it through an appropriate hologram to create whatever pattern I want. In this example, I'm choosing the Bessel Gaussian mode rather than a smiley face. So how do we make a pattern-sensitive detector? Well, we just run the process backwards, so in reverse. Why? because by the reciprocity of lights, the Bessel mode coming backwards through this hologram must return itself to a Gaussian mode. And if at the back end of this I put a single mode fiber, only Gaussian modes fit into a single mode fiber. And so the combination of this hologram in reverse, like the conjugate essentially, with the single mode fiber makes what I call a pattern sense. And so now we have all the building blocks of doing quantum mechanics with patterns of light. We have the crystal that generates the entanglement, and we have the detector to look for the patterns. And the first person to do this was Anton Zeilinger's group about 20 years ago now. And what did he do? Well, he didn't have spatial light modulators, but he had hard-coded holograms. So you see his cartoon, very similar to mine. He's going to pump his crystal, generate the two photons, and he's going to measure in the orbital angular momentum basis. And what he did was he also changed the OEM of the pump. So if you look at the middle panel, when the pump had no OEM, indeed he found this diagonal. You know, if photon A was 2, then photon B was -2. And if he shifted the pump by giving it OEM, then again the diagonal shifted to add up back to the pump again. So this was a very seminal paper, and it was the first demonstration of entanglement with spatial modes of light. Very, very important to drive the field forward. So we're going to repeat his experiment, only this time instead of diffractive optical elements that he used, we're going to use our spatial light modulators, and we're going to have a digital hologram for photon A's control and a digital hologram for photon B's control. So remember I told you about those grayscale pictures? So that's what I'm going to do. I'm going to have grayscale pictures with the spiral phase, and I'm going to change the spiral phases on A while measuring on B. So for example, if I pause at this case, I'm asking, is photon A +1? So it's going from black to white. And is photon B +3? Because you see there's 3 of these branch points. If the answer is yes, I will get a click. And if the answer is no, I get no click. And so then I look at what happens of photon A versus photon B. And here is a typical result from our laboratory. And you see that we have indeed a very strong anti-diagonal. So photon A was measured to be 10 units of orbital angular momentum. Then photon B is measured to be -10. So this doesn't confirm entanglement, but it does show conservation of orbital angular momentum down to the single photon level. And now if you didn't know it before, I can confirm for you that infinity is about 20, at least in my lab. Now, the students in the audience, you're probably saying, wait, what? 20 is very, very, very far from infinity. It is, it's true, but it's also an order of magnitude bigger than 2, which is what you get with polarization. So although there are some practical considerations that limit the bandwidth of the OEM, and it's not -infinity to +infinity, it's still sufficiently high that it makes it very attractive relative to polarization. And of course, you can tune the number of modes by playing with the experimental parameters. So it's not strictly -20 to 20. This is just a typical example. All right, we don't know if any of these states are entangled, and so we have to now go on and say, where do we see the entanglement? Well, one way to do it would be to do what Elaine Aspect did back now 40 years ago.
One quick question. So
sure.
Regarding that infinity, what do you think is a major factor? Is this a fiber, the way we detect? As to what limits how many modes one actually sees?
It's the P0 contribution of the hypergeometric mode expressed into the Laguerre-Gaussian basis. So the signals keep getting lower and lower, and eventually you're into the noise. You can make it much wider by having smaller, narrower crystals. So go more into the thin crystal limit, and you can better by having a small down-converted blob of light relative to the detected blob of light. So all these things would let you extend the bandwidth, but you would always come into the fact that it falls off because of this P0 component. And you're absolutely right. It's because we're coupling into a single mode fiber. So that is the limiting factor. It will always fall off and eventually you'll always hit the noise.
Okay. Okay.
Yeah. So we want to confirm entanglement. We can do what Elaine Aspect did 40 years ago. And you probably have studied this in your quantum mechanics course, but I'll remind you again just in one slide what the idea is. So the idea is to measure a conditional probability. Given that I chose to measure something on photon A, over here, what is the probability that I measure something on photon B? And what Elaine Aspect did with polarization is he said, let me try to measure, this polarization state on photon A, and I'm now going to, turn my polarizer on photon B and say, okay, what's the chance I get some counts as I do this? And if you do the math, it's very interesting because if you have classical correlations between the two arms, then the signal that you get, this is actually for this calculation for polarization, the signal you get oscillates around the quarter mark, around 0.25. It never goes to 0, never goes to a half. But if you have quantum correlations, see that the curve looks quite different. It goes from 0 to a half following a nice sinusoidal curve. So just visually, without doing any analysis, you can immediately see which case you have. And when he did his experiment, this is what he got. And well, I think we can all agree that, of course, there's some experimental uncertainty. I mean, you must remember it was 40 years ago. We can agree that it's certainly this case, right? It's going from 0 up to a half. And so for sure, he had quantum correlations. And actually, I like to tell people that this is my favorite experiment in all of physics because it's the only one I know of where in one experiment, you can eliminate 25% of all physical theories. So if you divide up the physical theories of the way nature works into these blocks in terms of unique or multiple realities or local and non-local interactions, then his experiment removes this block entirely. It can't be possible. And so that's very impressive. I hope one day I can do an experiment that also eliminates so many possible physical theories. So what we can do, of course, is we can repeat his experiment, but this time, instead of turning polarizers, we can turn holograms. So we can rotate one hologram, one arm, while keeping the other one fixed. That is also a conditional probability question. You have to choose the superpositions with some rules. And if you do that, then this is an example for Bessel beams from our lab. And you see again, the oscillations are from 0 to a half. And there are different curves according to the types of superpositions that we choose. And from this data, you can look for a violation of a Bell inequality. And here you see the violation. So this is your first confirmation that there is some entanglement in the system. There are other things you can do to probe what's going on with these photons. For example, you could do a Homomandl experiment to look for distinguishability of the photons. I'll remind you again that they bring two photons onto a beam splitter, and I will actually do this a little bit later for you. And they look to see whether all the photons go one way, all the photons go the other way, or do you get one in each arm? And if you can't tell the photons apart, then you never get one in each arm and you get this dip. So if you look at the coincidences, you get 0 coincidences if you tune the arms very carefully. And now you can do the same thing with orbital angular momentum. So here is, again, a nice result from our lab. For different OEM, you can indeed get this Homomandl dip. But these are all kind of indicators of the entanglement, but they're not really measures of the entanglement. So a true measure of the entanglement might be a quantum state tomography. And in this process, the idea is to try to unravel a very complicated unknown quantum state, remembering that you're only allowed to measure, once you make a measurement on the photon pair, you destroy them. So you cannot make multiple measurements on the same photon. So what that means, and I like to use this cartoon to explain the idea, imagine I have a very complicated object, but you can't see the whole object. You're not allowed to. But what you are allowed to do is you can have a torch and you can look at the shadow that the object produces on some wall. So you could shine the torch this way and maybe you see this shadow, and you could shine it that way and you see a different shadow and so on. And now I tell you, you can shine it at as many different angles as you like. You're only allowed to look at the shadows. Can you work out what the object is by just looking at the shadows? That's what a quantum state tomography does. By multiple projections, measurements on the states, you try to work out, knowing the answer to every question, what must the state be? And that's what the process is about. And to get an idea of, what sort of projection should you make, it's very instructive to go back to polarization. And this is something that Miles Paget and his group did many, many years ago. So what Miles did is they said, okay, look, if we were working in polarization, what would we do? Well, we can look at the polarization states of photon A, and we can look at the states of photon B, and then we can just write down in this matrix what sort of things we would do, for example, for a Bell measurement or quantum state tomography. And the tomography would be the two orthogonal states with their superpositions, taking all the different counts. And then what Miles said was, okay, look, in a two-dimensional basis of orbital angular momentum, what would be the equivalence? And the argument says, well, let's say that the right-handed and left-handed polarization states are the same as say the +1 and the -1 OM. Okay, how do you get the linear states? Well, you get them by superpositions of these two, right? So then he said, okay, in that case, the equivalent projections for OAM would be the superposition of these two OAMs. And if you take the superposition of the OAMs, you just get the Hermite modes. And just like the polarization is rotating, so the Hermite modes rotate. So this little lookup table was very, very useful in the early days of quantum state tomography to work out what should we do. And so here's a result from their paper. They said, okay, look, the orthogonal states for polarization are the OAM states. The mutually unbiased states or the superposition states are just these kind of binary holograms, which are going to be rotated. And so now we can take our measurements and extract a density matrix. So to make it more explicit, imagine I have holograms for +3 and -3. Then the superpositions would just be the superposition of those two, which gives you this like cosine type grating. And this thing is rotated. So you take all these measurements, you can see that there's 6 different combinations. So there's going to be 6 measurements on photon A and 6 measurements on photon B. And if we look at all the projections, we try to work out what would be consistent with these answers. And that's how you get the density matrix. Density matrix, you can work out anything about the states. For example, its fidelity and so on. So this is a good indication of what's going on. And what you can do, and something we worked quite a bit on in the early years, is to generalize this to higher dimensions. And you can do that by taking the Pauli matrices and generalizing them to Gell-Mann matrices. I don't want to go into the details, it's a little bit technical, but the essence is simply to move that same concept from 2 dimensions to higher dimensions. And here you see then a high dimensional, here's a high dimensional tomography, so it's lots and lots of measurements, and here is the density matrix outcome. The problem with the tomography is that it can take a very, very long time. It can take weeks for dimensions in the order of 10 to 20. It can take years and years for dimensions in the order of 100. So that's absolutely impractical as a tool to probe a quantum state in real time. So very recently, we dreamt up a way to get around this. And what this method does is it kind of takes some of the benefits of the Bell measurement and some of the benefits from the tomography, blends them together to give you a very fast estimate of how many dimensions do you have entangled in your system and to what purity. So again, it's a conditional measurement. So you rotate some measurement on the one arm while measuring something on the other. And so you get these visibility curves. And so you can work out the visibility of this. And you change the holograms. And so you get many visibilities. And the idea is that what makes it work is that the dimension, which we denote by K, and the purity of the state. So a purity of 1 means ideal, no noise, and a purity of 0 means you just have noise, okay? And the purity of the state, that it turns out that they're monotonically increasing functions of the visibilities that you see if you construct these projections in the right way. So if they're monotonically increasing functions, it means that if you measure a particular visibility shown by this slice through the curve, then everything on the solid red line would be a solution. So from one measurement, I can't tell you what the K and the P is, but I can tell you that it has to sit on this curve. But then I can change the holograms, repeat the measurements, and now I get a different solution space. But it must still be consistent with the previous one. And that's what you see up here. By doing this with several different visibility holograms, and you don't need too many of them, you can see that there's only a single region where they kind of all agree. And that must be the answer to the question. And so in this instance, it happens to be about 22 dimensions with a purity of about 45%. I should tell you that the purity was made deliberately low. So we deliberately introduced noise to the system so that we could demonstrate the principle works for mixed states and not just pure states. So this is a very fast method. You can do it in minutes. And the idea is that it would be a quick test to see what the situation is and then follow it up with other methods. For example, Nihel's cool methods of just using a few bases to do the tomography. Okay. So at this point, I see there's a hand. Let me just finish the sentence and then we can maybe take a question or two. I also want to have some water. So at this point, we've got our entanglement working. The detectors work. We can verify the entanglement. And so what we're going to go on in the next 10 or 20 slides is to use now our patterns of light as a basis to see what can we do with them. Okay, on that point, let me take a moment's break and I'm happy to take a few questions and then we can carry on. Okay.
Yes, I have one question here that regarding of the purity and the dimensionality. Is that a number of measurement is fixed for any dimensions? Means here I can see that 1, 3, 5, 7, 9, and 11. And why specifically these odd numbers has been chosen?
Yeah, it turns out that that odd combinations converge much faster. And as for how many you need, it's quite convenient. What happens is that the visibility starts to decrease as you increase the numbers. And at some point you can see, there's no point in going beyond this because there is no visibility anymore. So typically, without knowing anything about the states, we find that you have to use about 5 different analyzers. And the recipe is very, very simple. To construct the analyzers is very, very simple. So, and also one more thing, we did this for orbital angular momentum, but also for the pixel basis. So this recipe is not dependent on any basis. It just has to be a spatial basis. So pixels, OEM, Hermite modes, it doesn't matter, it will work for all of them.
Okay, and then another means I want to ask some technical questions that how means when you said that one hologram fixed in one arm and in another arm you are rotating that holograms. So is that rotating that hologram means that you are introducing an additional e⁻IL theta amount of phase or something?
Very, very good question. Brilliant question. In the orbital angular momentum world, a rotation is a phase change. So it is a physical rotation in the orbital angular momentum world. But in the pixel basis, so we did this also for pixels, like literally pixels across the screen, it's not a physical rotation, it's a relative phase between the pixels. So it's a rotation in some space, but not a physical rotation of the hologram.
See, so, but the question is that if e⁻IL theta is there, then is it a flat phase or it is some helical phase is introduced, and then how it is coupling to the single mode fiber?
Oh, so you're talking about going back to the detector?
Yeah.
so if you have, okay, so if you have, say, a helical phase of that's clockwise, if I pass it through, say, a glass optic that has an anti-clockwise winding, then it will unravel the clockwise winding, so the product of the two is 0. And then you have you have a flat phase straight after the hologram. You still have the donut beam phase. And if you do the math, you'll see that that converges into a blob of light that will be Gaussian-like. It will not actually be a perfect Gaussian, but it will be Gaussian-like. And that goes into the single mode fiber.
Okay, thank you very much.
All right, let's continue, and then we can take a few more questions later. So what is the benefit apart from the higher dimensions of going to patterns of light? And the benefit is that you can use the degrees of freedom of light to tune the entanglement. So for example, here we're making Bessel beams. You see these rings, they generate Bessel beams of different orders. And if you look at the OEM spectrum that you get, of course, it looks different to if you just have the normal OEM. So you can, for example, flatten the spectrum. So this is using the radial degree of freedom of Bessel beams to control the OEM spectrum and therefore control the dimension. The same with Laguerre Gaussian beams. You can use the radial order P to control the spectrum from very narrow to very wide. And you can not use radial or azimuthal modes at all. You can use Hermite Gaussian modes. And so now you see that in the OEM basis, you use Hermite Gaussian beams, it's very complex structured entanglement. So you can tailor how the entanglement looks by choosing the way you make these projections. You can also tune the size of the modes. So for example, Laguerre Gaussian or Bessel Gaussian or Hermite Gaussian, they all have a wavefront that's got maybe some radius of curvature. They also have a size. By tuning the size of the mode that you're trying to detect, you can also tune the dimensions. For example, a very bad choice of size gives you a very narrow amount of OEM, and a better choice of size gives you a very wide band of OEM. And so you have a lot of control using all the parameters within the spatial degree of freedom, which you don't get with polarization. So that's the first benefit of using spatial modes. The next benefit is that some of the properties, the classical properties of these spatial modes carry over to the quantum world. So let's stay with the Bessel beam. Bessel beams are very easy in the classical world to create with an axicon. You just illuminate a conical piece of glass, and then where the rays interfere, which is this red diamond region, you form a Bessel beam. And Bessel beams have a very interesting property. If you block the beam, so you put an opaque aperture in the middle of the beam, what happens? Well, it turns out that some of the rays can bypass this aperture. And so there will be a shadow region where the beam is destroyed. And this gives you a minimum distance over which beyond this, what will happen? Well, beyond it, in the blue diamond, you know, the overlapping rays are fine. They kind of got past the aperture without any hassles. And so in this region, in a classical world, you should see the Bessel beam again. And it's called self-healing. So this would be a classical Bessel beam. Here I've blocked the beam. And as I'm inside the shadow region, it's still very messy. But as you move out of the shadow region, you see that the Bessel beam is starting to reform. So now you can go to your quantum experiment and say, does the same thing happen? For example, if I block the entangled photons, not entirely, but just some region of them, and I project into the Bessel basis, would I find quantum self-healing? So this yellow region represents this minimum shadow region. So we would expect that beyond this, you would see the self-healing. If we project into Laguerre Gaussian modes, then you see that's the purple dots. We never get out of the noise. It always remains noisy. The coincidences is in the noise. But if we project into the Bessel basis, yes, we are in the noise when we're inside the shadow region, but as we go out, well, then we see that the coincidences rise very rapidly. So the signal becomes apparent out of the noise. And if you look at the density matrix, then initially it's pristine. Straight after the obstacle, it's completely messed up. But this is just because there's no signals, all in the noise. And then once we're outside the shadow region, the density matrix self-heals. It's that you can see the signal from the noise. And this is for a 4-dimensional state. And so you can have high-dimensional self-healing of quantum states. And you can see why that would be useful. So quite recently, we did this with QKD through obstacles. So you place an obstacle in the path of the photon, you try to do quantum key distribution, and if you project into the Bessel basis, you can recover the signals, which means that you can still have a key rate obstacle in this path. And I won't worry about the details of that. Okay, so some of the properties of classical properties translate over to the quantum. But all of this has been projections into some bases. What about engineering the states at the very beginning to be in some bases? So to do that, what you can do is you can go back to your cartoon of the experiments. And this time we're going to use the Homomandl Effect to engineer quantum states. Now, normally when you talk about the Homomandl Effect, we talk about it in the language of distinguishable or indistinguishable photons. But here, the two photons arriving at the beam splitter are entangled. And so a better way to speak about it is about the symmetry of the states. So if I look at the two photons that arrive at the beam splitter, I can ask, are those photons in a symmetric state or in an antisymmetric state? And if you do the math, it turns out that the antisymmetric states will give you one photon in each arm. So you would get coincidences. Whereas all the symmetric states would give you two photons in each arm. And because there are two photons here or two photons there, you can never get coincidences. On coincidences, you know that you must have an antisymmetric state. So how do we do that? Well, in one of the photon arms, we just add some Dove prisms. And you know what a Dove prism does? If you have two of them, it just rotates a picture. And as we discussed a few minutes ago, if you have orbital angular momentum, then a rotation of the orbital angular momentum states is a phase change. So I can introduce a phase change by just rotating the states. And of course, I can make that phase change the state from symmetric to antisymmetric. And now I'm going to do something a little bit different. Rather than just look at the coincidences after the beam splitter, I'm actually going to put my spatial light modulators here so that I can do projections in the two photon arms. So it kind of looks like what I had before, but if I block out all of this, then this is a state preparation step. And now we can see if it works. So if I come in with a symmetric state, which is what you get from the down-converted process, then sure enough, you get the Homomandl dip. This is for L plus minus 1, by the way. But if I turn the Dove prisms to tune that state to be antisymmetric, so the antisymmetric version, then the dip turns into a peak, because now I have coincidences going in the two arms. And the symmetry and the coincidences that I get at the back end of this device, which means that I can make different subspaces appear symmetric or appear antisymmetric. In other words, to be filtered out or to let them pass through. And to give you an example of that, let me go to this slide. Initially, I'm looking at 3 subspaces in a 6-dimensional space. 2 of them are odd. It's plus minus 1, plus minus 3, and one of them is even, plus minus 2. If I don't have any Homomandl filter, of course, I get all the states. But if I tune my Dove prisms to cut out, say, all the even states, then look at what I measure. All the blue peaks have disappeared, and the density matrix that's left only has the odd peaks, so the antisymmetric peaks. And so this is a way of tuning or engineering high-dimensional states by quantum interference. And it's a very useful tool because this projection onto an antisymmetric state is exactly what you need if you want to do entanglement swapping. So before you look at the big cartoon over here, look at the little picture at the bottom. It's going to explain the idea. And this is a textbook idea, I would say. It's not our idea. So the idea behind entanglement swapping, at least one of the realizations, is that imagine you have two entangled photons, A and B, and independently another pair of entangled photons, C and D. And you would like to establish correlations between A and D that are initially independent. Well, how could you do that? What you do is you take photon B and photon C and you send them to a beam splitter. If you get coincidences because one photon goes out on each path, it means that you must have an antisymmetric state. And this Bell projection over here allows you to establish entanglement between the two independent photons. So our realization of it looks like this. It's the same as before. We have two nonlinear crystals, each one generating photon pairs. We take one photon from each of the crystals and send them to the beam splitter to project onto this antisymmetric state. And photon A and photon D are controlled again with the spatial light modulators. And now we can choose in which basis do we want to see this entanglement swapping. And of course, we're going to choose our angular momentum because that's what we like, right? And so now we have a four-way Homomandl effect. So this is the dip. It's not perfect visibility, as you can see, but it's not too bad. And here is the two-dimensional density matrix for entanglement swapped orbital angular momentum states. So that all works very well. In fact, it's limited to 2 dimensions for some very technical reasons, fundamental reasons actually. And if you watch the archive in about a week, maximum a week's time, we're going to put a paper on that shows arbitrary dimensional teleportation and entanglement swapping with OEM. So we've overcome this 2-dimensional limits in the meantime. All right, so what can we do that's fun? And I want to use this example to go away from orbital angular momentum, although I'm going to use it for the explanation. So I have photon A and photon D now entangled. They were originally independent. And what we were wondering is, okay, what if I do some ghost imaging? What if I put an object over here in photon A? Could I see an image in photon D? You know, when ghost imaging is done, it's usually with thermal lights, entangled photons, so they already have spatial correlations from the entanglement. But in this case, A and D were initially completely independent. And so how would the ghost imaging work in this instance? And the theory is very, very interesting. The theory says that if you have an antisymmetric state that you project onto, then if you have an object of a lambda, the image will be the contrast inverted lambda. So everywhere the lambda was bright, it will be dark. And everywhere you had no light, darkness, it will be bright. But it's only for these states where the indices are different. That's the antisymmetric state and this particular element of the symmetric state. So those two. All the other states where the two indices are the same, the image is the same as the object. So if you started with a bright lambda, you will end up with a bright lambda. And in fact, if you add up all the symmetric states, because two of them just do the normal thing, it kind of cancels this other one. So the symmetric states on average also just do the normal ghost imaging. So the prediction is that in an antisymmetric projection, you should see a contrast inverted image. And why would that be the case? So let's go back to our OEM to understand it. So here's the cartoon of the entanglement swapping. I have 2 crystals, each generating 2 photon pairs, or each generating 1 photon pair. So I've got 4 photons. And imagine they have 0 OEM pump. If I measure on my spatial light modulator this photon to be -2, then the photon that's going to go to the beam splitter must be +2. All right. Let's say I try to measure +1 on the other side. what would the photon that it sends to the beam splitter be? It would be -1. Can you make an antisymmetric state from a -1 and a 2? Yes, you can, because they're not the same, so that's no problem. They have to be different to get an antisymmetric state. They can't be the same, so that's fine. So what I send here, this would give me clicks, it would work. Let's try a different case. Let's say I still measure -2 here, so that means that +2 went to the beam splitter. Let's say I also try to measure the same -2 on the other side. Well, then it must also send +2 to the beam splitter. You see that these two indices are identical. You cannot form an antisymmetric state if the indices are the same. They have to be different. So that's not possible. And so you see that if you try to measure the same thing on the two arms, you can't get any coincidences. That means that what you prepare here, you don't get on the other side. In fact, you get everything, but you can get anything at all except the thing you tried to send. So in the ghost imaging world, usually an object of a lambda gives you an image of a lambda. But here, an object of a lambda will give you everything except that. So if you have a bright pixel here, you must get a dark pixel, everything except the bright pixel. And if you had a dark pixel over there, you must get everything except that, which is a bright pixel. And when you do the experiment, it does exactly that. If you have an object that's got, say, the left pixel switched on, the theory predicts that the left pixel should switch off and the right pixel switches on. And that's exactly what the experiment does. And it does it in no matter what pixels you choose. It's limited in the dimensions you can go to because of this two-dimensional restriction, but in principle it works. Okay. All right, I think what I'm going to do, because it's 1 hour in, am I allowed 10 more minutes just to wrap up, or would you like to stop and have some questions now?
That is fine. I mean, you can take 10 minutes, yes.
All right, great. So I want to, are there any questions from the students, or shall we just have a wrap up the last 10 minutes?
I think we can save it for the end now. Huh?
Okay, all right, good. So I want to just end by, by showing you one last thing. And I think I'll skip the last few slides because I've been talking a long time now. So far we've always been saying, look, rather than polarization, let's use patterns of light. So instead of this, let's go to this. But in fact, you can take the tensor product of these two fields and use both of them at once. And we call these vectorial fields, and you guys are also experts at understanding this. So now, you know, you not just get the OEM, but you get OEM with spin states, you get superpositions, which give you, for example, radially polarized light or azimuthally polarized lights. Why is that useful? Well, for example, in communication, you have a natural four-dimensional space. You have these vectorial beams, which are four-dimensional, and the mutually unbiased bases would just be the orbital angular momentum beams given below. So combining degrees give you a lot of versatility. They're easy to make. They're also easy to detect. I'm not going to bother about the details, but they're very easy to detect, which means you can do QKD. And so here you see the four orthogonal states and the four mutually unbiased states measured and detected. You can use this as an encoding scheme of encoding some information, encrypting it, and decrypting on the other side. And what we showed is that, in fact, if you have a deterministic detector, you can really get a very high Q rate. I want to say that actually this work came out the same time as Ibrahim Karimi's cool work. He did a really nice experiment across about 300 meters in Ottawa. Really, really nice stuff. And he used the same basis and showed really in a real world situation that it works. So you must go and have a look at that work. There's another cool reason for using these vectorial beams. I'm not going to talk about classical entanglement. I know, again, that you guys are been studying coherence and classical fields and quantum fields very carefully. But, you know, we have done a lot of work in this idea of classical entanglement, and I don't want to get into the debate about to say that it can give you some advantage. So if you look at this cartoon, here are my two entangled OEM photons, and I send photon A through some noisy channel, can be turbulence. Then obviously photon A is perturbed, right? Now imagine I do an experiment where I have a vectorial field, but this time it's not two photons, it's just 2 degrees of freedom. It's a bright classical beam. Degree of freedom A is the same OAM, but degree of freedom B is polarization. Well, if this noisy channel is not birefringent, for example, like the atmosphere, then degree of freedom B is not affected. And so only degree of freedom A is affected. And in fact, this little cartoon suggests that the way the vectorial beam decays should be identical to the way this entangled state decays. And you can do that experiment. In this case, the horizontal axis is changing the degree of turbulence. So 0 means very strong turbulence, like a very noisy channel. And 1 means, pristine channel. And the vertical axis is measuring the concurrence. So what does the decay look like for the entangled states? And what does the vectorial decay look like? And you see that nature can't tell the difference between the bright vectorial beam and the quantum entangled states. And that's very relevant to you to probe the channel with a bright classical beam and use the information to correct your quantum states. And if you do that, instead of seeing your quantum state decay, you can actually bring it back up to very, very high fidelity without having to make a measurement on it. So that works very well. I'll give you one last example, and then I'll wrap up the talk. So here's my hybrid entangled state again, orbital angular momentum and polarization. But let's focus on each photon. So photon A is entangled in OEM, or photon 1 in this case. Photon 2 is entangled in polarization. What about the other degree of freedom? Well, the OEM, so photon 1 at the bottom here, is just linearly polarized. Photon 2, which has got the polarization entanglement, is just a Gaussian beam. So entangled in 1 degree of freedom, but just a simple state in the other degree of freedom. Well, a Gaussian beam can go through a single mode fiber. So if you generate this hybrid states, you can send the Gaussian polarization down the fiber, but keep the OEM entangled photon in free space and modulated with the spatial light modulator. And what does this do? It means that at the back end of the fiber, you don't have a high dimensional state, but you have multiple 2-dimensional subspaces, because you can change the OEM from ±1, ±2, ±3, and so on. And so rather than just 2 dimensions of polarization or the perfect high dimensions of OEM, here you have 2 times n, where n is the number of subspaces you would like to use. And so we've shown this down 250 meters of single mode fiber, and more recently 25 kilometers with QKD. So that's a cool thing you can do with hybrid states. And in my very, very last example, QKD is really cool, but in the modern world, we don't want to talk on networks where we are speaking just to one another. We want to share information across nodes. So rather than share a key with one person, I'd like to send part of the key to one person, part of the key to another person, and many, many people. And if they trust, so this person's got half the key and this person's got the other half, then let them share the key. So QKD, of course, we communicate peer-to-peer, but in this case, it's called quantum secret sharing. It's a different principle. And I'm going to do it now with hybrid states. And I just want to explain to the students in the audience how this works. So imagine the secret I wanted to share between 2 people, if I trust them, is, say, the y-intercept of the straight line. Well, then what I could do is I could let the 2 people make measurements on their system. Don't worry about the details. If the measurements don't sit on my straight line, I tell them to discard that measurement. But occasionally they make measurements that is on the straight line. And I say, okay, those ones you keep. So have a look at what happens. Bob has got the green points. If you have 1 point on a straight line and you're trying to work out the intercept, you can't do it. But if you have 2 points, of course, you can work out anything about the straight line, right? So if Bob and Charlie, who each have a point, trust one another, then by working together, they can work out the secret. And that's the idea of quantum secret sharing. And I wanted to use this final example to explain what we really do in our group and in our lab. So what we really do is we try to understand how to turn a protocol into an experiment. So in this instance, we want to do quantum secret sharing in 3 dimensions. And we're going to use a hybrid state to do it. So the first question is, how do you prepare such a state? And that's what we try to work out. And the next question is, how do you do the unitaries that Bob and Charlie must make in order to, get onto the line? And that's what we try to work out. What optical elements will make this happen? And then finally, how do we do the detection? How do we take the concepts that we know from the board in theory and turn them into a practical setup? And here you see, because we have hybrid polarization and patterns of lights, the measurement involves polarization and, of course, spatial light modulators. And you can do the measurements and it all works. And so you can do this in any dimension you want. And we've gone up to 11 dimensions across 10 parties. So to wrap up the talk, I've been talking for a very long time. I'm sure you guys are as tired as I am. I want to tell you something that Bob Boyd once mentioned to me. I'm borrowing this analogy from him. I saw it in one of his talks. So what Bob said was, you know what? We're just using the patterns of lights. That's spatial information encoded in the spatial degree of freedom of a photon. But we've been using the spatial degree of freedom for many, many centuries. In the old days, people would wave flags as a way of communicating. And that's all we're doing today. It's a very fancy way of flag waving that we're doing in the lab. I've spoken for a long time, but I've only spoken on quantum. Actually, quantum is about 1/3 of what we do in our group. We also do a lot of work in lasers and general structured lights. So if you'd like to read a little bit more about that, please go and have a look. I also haven't had time in this talk to cover all the wonderful work done by others, including your supervisor, who's done very seminal work on, angle, OAM, uncertainty principles and violations, really fantastic stuff. So there's wonderful, wonderful work out there. Go and read the reviews and see what people have done. Quite recently, we wrote a review. It kind of summarizes what I understand about structured lights. So if you'd like to know more about that, then go back a few months in Nature Photonics and you should find it quite easily. So that leaves me to thank my collaborators. We love to collaborate with people and great collaborators across the world. And I want to tell you that, like you, we're a young, vibrant group. We love to have visitors. We love to send our students out to other groups. I think that's the benefit of science, is to work with other people and experience other ways of doing things. In a normal time, non-COVID time, we typically have about 10 visiting students from around the world, and we send about the same number out. So take this as an invitation to you that we would love to collaborate and have such an exchange. And on that note, I'm sorry for talking for so long. I hope it wasn't too fast or too simple. And thank you very much again for inviting me to speak here.
All right, thank you so much. I think this was very, very exciting and again, motivational. This is so we have time for a few questions. Abhinandan, you go ahead, unmute yourself and just go ahead with the question.
My question is related to your work in that tomography where you have measured Schmidt number and purity. So can you just go back to that slide?
Sure, no problem. Let me share my screen again. Do you see the slides?
Yes, right now I can see the last.
Yeah, I'm going to, what I'm going to do is just go back like this, it would be faster.
Yes.
All right.
I guess the visibility is the visibility of this P you are mentioning. So how you are constructing those 3D curves and this blue
Right.
curve and the red curve from a single end measurement?
Right. So the blue curve comes from writing in arbitrary states, but you have to choose a basis. So let's say you chose OM and you said, okay, you know, how, if I made these particular projections, how would the visibility of the outcome, so there's a particular outcome, how would that visibility change as the dimensions and purity changes? And the theory is very simple. It's in the paper. What's important about it is that it's monotonic. That's all. Now, we can show theoretically that it will always be monotonic, assuming that your noise is isotropic. So essentially you have the isotropic states. What we're trying to do now is to generalize that to arbitrary states. For example, Vanna states. Could the same technique work regardless? We're still working on that, but if you have the isotropic state, which covers most cases, then for sure you can see how the theory works and will always give you this blue curve. And now the question is, where is your measured visibility? So this transparent slice through is the measurement outcome. So let's say this visibility is 90%. I don't remember exactly. That would be like this point, 90%. So that means that's the solution space.
Thanks. I have another question regarding this paper. I have actually gone through it, and in one of the sections you have mentioned about entanglement dimensionality, which is a little bit different from K, which is a dimensionality of the Hilbert space. So can you just a little bit explain what that entanglement dimensionality give more information about entanglement, or is it like how it connected to the quantifier?
Yeah, we've been talking a lot with Marcus Huber, and you know, he's done a lot of work very recently on noise, understanding noise in high dimensional entangled systems. And one of his results, actually, which is a little bit hidden in the supplementary information, is that if you measure the number of modes involved in the entanglement, you can get quite a high number. But if there's quite a lot of noise involved. So how many useful dimensions do I have? If I can just talk colloquially. And the useful dimensions is this kind of the other definition of the entangled dimensions. So in the paper, we use his definition. And if you look at the useful dimensions, it of course drops very rapidly if you have a lot of noise. So those are the two ways of looking at things. Most people in our community would just use K, but he's trying to get people to swing around to another way of thinking about things. He doesn't agree actually that K is a good measure. So yeah, so that's why we showed both in the paper to kind of point out the relevance and importance of understanding noise a bit better.
Okay, thanks. I have another question regarding that self-healing that you have shown in a PDC process.
So I have one question here on the same slide. Maybe, Abhinandan, is that fine if I go? Just one quick question.
Yes, sure.
So the question is, you have this K and the P, this purity. So the purity that you're talking about here, is that the two particle purity or is that one particle purity?
So this is the purity as is defined as P times the P, and 1 minus P gives you the noise part of the states. So we define an isotropic state that could be mixed. Well, it is mixed if you don't have purity of 1. And so 1 minus P is, what is the noise contribution, isotropic white noise to the quantum states?
So, I mean, theoretically, how do you, I mean, here, I guess you have the states in higher dimension, not just 2. So
yes, that's right. Yeah.
How do you calculate purity, or is it, I mean?
So, right. So what it comes down to is if you have the states, so imagine 2 terms to your quantum density function. Mm-hmm. One part is pure. Mm-hmm. So it's let's say your SPDC state times P, and the other part is noise, and it's times 1 minus P. Mm-hmm. What we do is we say, okay, We don't know what K is and we don't know what P is, but through this semi-tomography, we can now work backwards from all the visibilities and say, okay, what must the K and P be in order for this density matrix to be consistent with what we see? And so that's how we extract it. We extract it by a kind of fitting routine. It's the intersection of all these possibilities.
So these are the experimental purity.
Yes.
Okay.
Yeah, this is experimental purity. So what we did actually in this experiment is we kind of switched on the lights sometimes to make the purity drop dramatically. We would pump up the power of the pump laser so that we know for sure we're introducing like double counts and extra noise. So we deliberately introduced noise into the system so that we could tune the P.
Okay.
And then see what it does to the whole states, including K. Yeah.
Okay. All right. Thank you. Abhinay, then you go ahead with the next question.
In this same context, I have a question for a mixed state. Is this Smith number does give any information of entanglement? Because we typically use Smith number or K for a pure state. So is it also give some information of entanglement when it comes to mixed state?
Yeah, that's why I think that relates to the question that came just a few before this one. So you're quite right. K is the dimensionality of the pure part of the states. And that's why we have this extra definition, which is kind of the useful entangled dimensions, which is not the, and that decreases with the purity. Okay.
And so I have seen that you have taken a pure state, then add a part of noise. So can we, if we have a mixed state, which we are not introducing any noise that comes from some randomness or some turbulence, can we extend that method in that direction?
Good question. As I said, we are trying to look at that. But I think it's an open question. So, you know, if you've got some ideas on that, by all means, have a bash. We gave the students the problem of looking at the Vanna states. Could you generalize this to Vanna states? But your question is absolutely relevant. You know, what if you had modal noise and not isotropic noise? Would it still work? I think it would work, but it would need a little bit of theory to confirm it. So yeah, it's an open question.
Okay, thanks. I have another question regarding, can you just go to that self-healing where you have done some experiment with SPDC?
Okay.
Yes. So is it that I think this next slide talks about the, I think, entanglement. Is that the, is it after a certain propagation distance, does the entanglement comes back and then it remains same?
So the way we interpreted the results is that it's not that the entanglement kind of disappears or is destroyed and then self-heals. The way we phrased it is that, and also the way I explained in the talk, is that, of course, entanglement can't just reappear in a free space system. That isn't possible, right? You know, the entanglement in the system must be the same. But what changes is that your signal is entirely in the noise. So after the obstacle, you don't have a signal. So you cannot say whether it's entangled or not. But as you come out of the shadow region, the signal in the Bessel basis re-emerges itself. And so in the Bessel basis, you can recover the signal. And because you can recover the signal, you now have enough information to probe the state properly again. And so there you can see that, yes, indeed, the entanglement is back to what it was. If you choose a different basis, it doesn't recover so well. So if you could somehow remove the noise, then you would be able to find the entanglement. But of course, the system, you can't do that.
Okay. You have a question? Oh, Abhinandan, you have more?
Yeah, I have one more.
Okay, fine. Go ahead.
This is, can you just go to that imaging with entanglement swapping slide?
Like this one? This one?
Yes, this just before that one.
Okay, I'll go back to it.
So just my question is that here we have seen that the image gets inverted. I mean the black region,
Yep.
black becomes white and white becomes black. So also in that situation, does the position correlation between this two parties play any role regarding the resolution and all?
Yes, no, it does. So in fact, we worked out, although I gave a heuristic argument based on OEM about why it works, we have a full theory. In fact, where's the references? Yeah, in these papers, not in the New Journal of Physics one, but in the bottom one, we give the full theory about how the position correlation. And in the New Journal of Physics, we also have a full theory on what happens to position correlations when you have these Dove prisms to select the symmetry, and when you go through the beam splitter, what happens? And some very strange things happen. But we can predict theoretically from a position basis, like you've just said, that you must see this contrast inversion.
Okay, thanks. I'll definitely go through it. Thanks.
Right. Srinu, looks like your talk and work is very popular and famous here, just like A.B. de Villiers batting. So, but Srinu, one more question. You can go ahead, Srinu.
Hello, sir. The talk is very nice. So I have one question. What are the speed for the DMD switching?
So, yeah, so let me start with the spatial light modulator. The spatial light modulator goes at about 60 hertz. If you play some clever tricks, you can make it go up to some hundreds of hertz, but most people don't do that. The DMD, on the other hand, easily goes to kilohertz without any problem. So it's very, very fast, and it's very, very cheap, but it's very, very, so the efficiency, of the DMD is about 10%. Whereas the SLM, if you take everything into account, all the problems, it's probably about 65%. So you lose efficiency, but you gain on the other things. So I guess it's a question of what's most important to you.
Okay, and followed up one more question. It is, so we are showing many versatility of using spatial modes and its applications in optical communications and QKD, but to make this spatial modes really to go and in the practical applications where information is handled very high speed, it's kind of, what are the problems really we need to address so that it will be spatial modes or really makes real-time applications?
Yeah, good question. Let me show you this slide. I didn't show it, but so, you know, in these sort of talks, one always gives the impression that everything is beautiful and solved and there's no problems. But as you just said, that's absolutely not true. You know, we know how to create modes in high dimensions, but we don't know how to detect them, at least deterministically. And you can say, but you can use a mode sorter for OEM. Yeah, sure. And what about the mutually unbiased species? So we don't know how to detect spatial modes deterministically beyond d is equal to 4. We can only teleport d is equal to 3. And that's with path, not even with spatial modes, because we don't know how to combine many, many photons with high efficiency. And then there are things like modal crosstalk in turbulence and fiber, which limits the distance to very, very short, hundreds of meters in free space, kilometers in fiber, very, very short. And the bit rates, the key rates that we've managed to achieve, that's Ibrahim and Alan Wilner and Bob and all the famous guys, I say it's basically zero. It's as close to zero as you'd like it to be, with spatial modes compared to the polarization community. So my message is that we have got a very, very long way to go to understand how to really use dimensions and how to really gain the control. And so my feeling is that our toolbox is still very empty. And that's why I think it's a very exciting field to play in.
Okay, what I feel is that the speed of the doing all this is completely not considered in all these applications that I feel.
Yeah, that's right. Because if we mention the practicality of what we advance, we'd never get our papers published.
Okay, thank you very much. One more last question. It is like the QKD, in the last you are showing that we are sharing the secret key to the multiple people. Where are you using photons of multi-photon entanglement kind of things, or is it only 2 photon entanglements?
Let me go to that. Yeah, in this case, it's a 2 photon entanglement scheme. And what happens is the 1 photon goes around the different parties. So in this case, it's sent to 10 different parties to manipulate it, but it's done in 11 dimensions. And I'll quickly show you another slide that I didn't show since you asked that question. It's also a very good question. Also, I sometimes end with this, but not this time. These little blobs represent literature papers, so what people have done in the community. And what you can see is that a lot of people have done wonderful dimensionality work, but with 2 photons, all the green bars, bubbles going up. And then a lot of people have done many photons, notably the PAN group, of course, but only with 2 dimensions. And so now you ask the question, okay, how many people move dimension and photons on the diagonal? And there are about 3 papers that do this. Mm-hmm. And so what I like to tell students is that, look at this. This is an empty void. We don't know how to control dimensions and photons together. And so here, if you want to find a space where nobody is working, here you go. It's completely empty. Of course, it's very hard, right? But you see, we don't have a lot of control. So yeah, we don't have multi-photon, multi-dimensional control yet.
All right. I think well, we will stop here. I think there's really fantastic talk, and several new things regarding the how structured light could actually be used. So again, let me, from everyone's behalf, let me thank you for this exciting talk. I mean, probably there were a few more questions, but I think we probably have to stop here. And again, since you have invited people already, so I think people who have questions maybe could email you. Will that be okay?
Absolutely, no problem.
Excellent. So again, thank you again so much. Maybe I and my group will probably be looking forward to some collaborative stuff, or maybe if we can take something, do something together. So
we'd love to do that. That'd be wonderful. Thank you again for inviting me. It was really great.
Thank you so much. Okay, bye.
All right, bye everybody. Have a good afternoon.